we've been talking about Q-learning, and we wanted to see how Q-learning, which is an iterative process, can be used to find a solution to the problem where you don't really have the parameters of Q for all the states beforehand. So as I said, initially you may have a bunch of states S1 to S4, S5 over here, and you don't really know what these values are, what these Q values are. And they're also interdependent. So you can only update this particular value if you know the values in other states, adjacent states, okay? So that's a problem. So what the Q-learning algorithm does is it uses the gradient descent algorithm to be able to figure out an optimal solution, okay? Now the question is, what are we trying to optimize over here? How do you find a solution if you really don't know what you're trying to optimize? What are we trying to optimize? Remember in the loss, we had a loss equation and we said that we're trying to minimize the loss. So we changed the weights and we took the slope of the rate of change of L with respect to W. And as we improved the W, we looked at how the change in the slope was impacting the loss. So the question is, how should we use gradient descent in this particular example to be able to calculate the Q values? Any thoughts? Any thoughts, anybody?
Sir, random weight initialization.
Okay, so we could start off with random weights, all right, just like we did with W. We picked any particular value randomly, but the question is how we were using the loss equation earlier to be able to find the minimum loss. What are we trying to minimize or maximize here?
We're trying to maximize Q.
Okay, so we're trying to maximize Q. Why are we trying to maximize Q? Why do you want to maximize Q?
To get the value.
I guess it's right here.
Reward.
Sorry?
To get
yes.
to the maximum reward.
Yeah, so basically, if you remember, we were trying to learn a policy. We said that the goal of reinforcement learning over here is to learn a policy that maximizes the expected cumulative reward. So in other words, what should this basically give us as a result of, once you've solved this reinforcement learning problem, what do we expect to get out of this?
The maximum cumulative reward for each state.
So maximum cumulative reward, so sorry, say that again.
For each state, and basically the final reward would be at the end of the whole process, right? So we want the maximum cumulative reward, but along the lines we also want to find the maximum reward for each state, because
but
that's what
the reward from each state depends on what?
Sir, we need to learn. Basically, given this reward, we need to learn.
So we're trying to learn the optimal policy, right? Is to learn a policy. The policy was what? It depended on two things.
On state and action.
State and action, right? So in other words, what we really want to know is for every state action pair, we want to know basically what should be the appropriate action to take. And we want to maximize the probability of taking the right action. Okay, so in other words, if we know that in this particular scenario, going up is the right action, basically we want to say that in state S2, the probability of taking of taking an action upwards should be maximum, right? So this should be something like 0.99 ideally, or 1. So that's what we're looking for. We're looking for, we're trying to maximize for every state and action pair. Or essentially what we're trying to do is for every state, we're trying to figure out what is the best action to take. Does that make sense? For every state, we want to figure out what action should we take so that we get the best policy. We get the maximum reward. Okay, so from here, what should be the probability that we go up and what should be the probability of going down, right? So in other words, if you think back to the MDP example, we said that, where was that? Somewhere over here. Yeah, so this was the policy that we're trying to maximize. So we basically want to figure out what should be these rewards over here. What should be these values over here, right? If I just use my. So basically what we're trying to figure out is that when you're in the good state, what should be your probability of maintaining it? So you clearly don't want to make it 100%, but you may want to have some probability associated with this, which gives you the maximum reward. Okay, so that's what we're trying to do. And that can be thought of as we basically trying to, if you come back over here, what we're trying to maximize, as somebody rightly pointed out, is we're trying to figure out, we're trying to maximize Q. Okay, and you're trying to maximize for every state, we want to be able to get the maximum reward. And if you take the optimal value over here, okay, we want to be able to maximize that. Okay, now remember when we were looking at gradient descent, it was called gradient descent, right? Why was it called GD?
Because it's find the minimum
Because we
value.
were decreasing.
Right. So this was basically based on the minimum value, right? So when you're trying to maximize something, what should we actually be calling it?
Ascent.
Yeah. So it should actually be called gradient ascent. We're not going to follow gradient descent.
Gradient descent.
We're going to try to follow a gradient ascent problem. Okay. Now, how would you? So if we look at the gradient descent, we basically, this is what we had. We had Wn plus 1, Wn. We took for minimum value, we took the R and the rate of change of L with respect to W. Okay. If you're trying to maximize it, then what should the equation be? So let's say if you're trying to maximize the weights, it would be Wn, and what would go over here?
Plus.
Yeah, so it would be a plus instead of a minus, because we're now trying to go according to the slope. So if the slope is positive over here, we want to go in this direction. If the slope is negative over here, we want to go in the reverse direction. Okay, so we use a plus sign over here. We again going to have a learning rate, and we're going to take dy by dt, or whatever this y is that we're trying to maximize. We're going to have that rate of change, and we're going to look at over time. Okay, so let's try to see where we go from here. So this is now where we are. We looked at the example of minimizing loss. So we said Wn plus 1 is Wn minus RL dl by dt. Now we're going to do something different. We're going to be maximizing Q. Okay, so we're going to take the old value of the Q. All right. And then we're going to use a plus sign because we're trying to do maximum gradient ascent. And we're going to use a learning rate. Now in reinforcement learning, you know, instead of using R, which is used for reward, so they use alpha. Okay, so this is simply the learning rate. All right. And then since we are looking at time, as we want to basically look at how we want to be able to maximize this over time. We're going to take the rate of change of Q with respect to time, okay, with respect to each step. So far this is fine. We're trying to maximize Q and we're going to use this equation, okay? Next, what we're going to do is we already have this equation. So we have Q new. Q can be written as the following. So it's got S and depends on S and A. The old value is going to be put in over here. Okay, so we're going to, the new value of Q is going to be based on the old value of Q plus the learning rate and the rate of change. Okay, and this is often called temporal difference because there are now two things going on over here. There's a temporal difference and there's also a spatial difference going on. So if you look at the previous equation over here, this is the equation that we looked at before. This equation wasn't a temporal equation, all right? This equation was based on states. Now, why do I say that? Because here what we're saying is that the Q value depends on other states, okay? So this Q value over here depends on the Q values of adjacent states, okay? So it depends on the Q value, the maximum Q value of where you will be in the subsequent time. So when you're going to another state, what is the Q value of that? Okay, so it's the Q value of adjacent states. And so this equation over here can be thought of not as a temporal equation, but maybe sort of a spatial equation, all right? It's more of a spatial equation because it is looking at the state space, okay? And it's basically saying how Q depends on other states, right? Now, when we try to maximize it, what we're basically saying is that we're going to use a temporal difference over here because we're trying to maximize this value with respect to time, okay? If anybody's confused at this stage, let me know. So these are two different ways of updating Q. One is spatial and the other is temporal. Is anybody confused with that?
Sir, I'm a little confused with the spatial one.
Okay, good. So let me repeat it. If you look at this equation, what were we doing over here? We were saying that the Q value can be calculated based on based on a certain movement. So this is based on movement. All right. And what we're saying is that the Q value is basically if you make a movement, you get a certain reward. In this case, a negative 0.1, and then you look at the maximum reward that you can get in the next state. Okay, so and this is the next state that you went to in the state at time t plus 1. Okay, this is the Q value that you got for taking a certain action, and you're saying what is the optimal action that you can take in the next state, in the adjacent state. Okay, and so if you go downwards from here, then the maximum reward that you're going to get is going to be the cost of the movement plus the maximum reward that you can going to get in the adjacent state. Is that clear?
Yes, sir.
Okay, and you can see that this has a spatial relationship. In other words, it depends on the direction that you're going in, and you're looking at the states in the adjacent state. You're looking at the Q values of the adjacent state, of the state that you ended up in because of this particular action.
Yes, sir. So it's based on the movement, right?
This is based on the movement. Okay. So now what we're saying is that there are two types of equations. The first one is the movement equation. And the second equation is basically saying, how do we maximize this value over time? Okay, so we're saying that we want for a particular state, you want to be able to iteratively maximize this over time, okay, using something like a gradient ascent algorithm. And now what we're doing is we're taking the rate of change of dq with respect to time, okay? So can you understand that this is a temporal equation and the other one was a spatial equation?
Okay, that was based on the movement. Now
Movement.
this is based on the change in Q, basically.
This is based on the over time. We want to be able to get a better and better approximation to the Q value. Okay,
Yes,
and
sir.
we're going to start off with a value of 0, and we're going to try to see if we can get a better and better value. Okay, and the way we're going to do it is we're going to be able to take the rate of change, okay, which is the rate of change over here. We'll use the slope and the learning rate. The learning rate will determine how far we jump. If it's too big, we'll jump very far. If it's too small, it will take too many values. Okay, so these are two separate equations. So far, so good?
Yes, sir.
Okay. Now what we're going to do is we're going to combine these two equations. Okay. And what we're going to say is that this was the previous equation, which was based on movement, based on states. And this is the equation which is based on time. Okay. And what we're going to try to do is we're going to combine these two equations. And this is the equation that we're going to try to get. We're going to be able to find out what is the value of dq by dt. Okay, because we don't know what this is. So what we're going to do is we're going to say that we're going to use this equation to be able to find out how Q is changing over time. Okay. Now, Q is being updated based on equation number 1 on the movement. Okay, remember this was the movement equation. And this was the original value of Q. And based on the movement, it got a new value, which had a certain reward and which had other, depending on Q of adjacent states. So can you see that this can be thought of as the rate of change of dq by dt? Does that make sense?
Yes, sir. But I would say why we are taking a max in this. This
Sorry?
could also be done with ST plus 1 and A. मतलब rate of change तो हम Q की next state पे और current state के difference पे भी निकाल सकते हैं. हम max के साथ क्यों निकाल रहे हैं?
देखिए max was already there. This was, if you remember, हम यहाँ पे क्या कर रहे थे? हमने यहाँ पे कोई change नहीं किया equation को. This was the original equation. This was based on the movement, and why we had chosen maximum. You remember why we had chosen maximum?
Yes, sir. Got it.
Okay, so the maximum was based on this movement equation. Okay, so we simply try to now combine these two equations. So now what we're doing is we're taking this the equation number 1, which already had the movement based on it. This is how we were updating Q, and this is the current value of Q. Okay, this is the new value of Q. And so this sort of represents the change dq by dt. So is that making sense?
Yes, sir.
Yes, sir.
Okay, good. So once you've understood this, now all we need to do is we update the value of dq by dt in this equation, in equation number 2. Okay, and what do we get? We get this equation, we take equation number 2, we take this value over here, we take qs of t, and now we take, we have alpha over here, all right, that's coming in over here, and we take dq by dt, which is from here, okay? So we plug in this over here. And dq by dt was this particular term over here, which is now what we have over here. Okay, So we're multiplying the rate of the slope over here with the learning parameter. So we have the learning parameter over here. We have the rate of change with respect to time over here, which is RT plus max this minus the current value. And so this is what basically the Q-learning algorithm is. This is how you're going to use it. And the best way to understand is by taking a simple example. Okay, but I hope that everybody has followed the derivation of this equation.
Yes, sir. But there's a little problem. Why
Sorry?
aren't we given in any, the one which is the Q value, the first value, which is ST plus 1 comma A. We are not given it time duration. Considering all others have a time related to all A's, but this A doesn't have a time.
What doesn't have a time?
RT plus max A Q ST plus 1 comma A. Not, it should be A plus T plus 1.
You're saying there's no AT over here?
Yes, sir. It's not related to time.
Can somebody answer this?
Yes, sir.
Okay, that's a good question. That's a good question. Actually, one of the reasons why it doesn't have an A over here is because we're using that to maximize it. But you could write it as A of t. Yeah, you could do that. So you're absolutely right. This is a good observation. So we could write it as A of t, and you could say that you maximizing it over all possible actions that you can take at time t. That's a good point.
Sir?
Yeah.
ये जो second equation है, ये आप बता सकते हैं कि ये किस तरह से draw की थी आपने equation?
ये वाली equation?
जी second वाली जो है ना dq over dt is equals to.
अच्छा ये वाली equation?
मैं थोड़ा confused हो गया.
ये वाली?
Yes sir.
Okay, so this is basically what we're saying is that the rate of change of Q with respect to time, what we're doing is we're using equation 1, which was based on spatial. Okay, so let's go back over here. We're saying that we're using this term over here. Okay, this portion was based on the movement. So Q was, whenever Q is updated, it is, this equation was based on the movement equation over here, okay, based on movement. This is Q S of t is how is it updated? It depends, well, if you make a certain movement A, take a certain action A, then there's a certain reward because let's say the movement cost, okay? And the maximum value that you can get from the adjacent state. Okay, so if you end up in the adjacent state, what's the maximum value that you can get from here? So your total reward will be the reward of going to the adjacent state plus the reward, because we're talking about cumulative reward, not a one-time reward. The cumulative reward is what cumulative reward that you can get from the state. Now, if you take this action going upwards, you get 0.8. If you go downwards, you get 0.6. Okay, so you take the maximum of either one of those two. So this is how we were calculating it based on the movement. Okay, ये आपको याद आ गया?
जी सर, ये मुझे याद आ गया. लेकिन वो जो आपने combine किया था equation को, वो part में confused हो रहा हूँ.
So the way we combined it is first we said कि we've got now this part you okay with, right? This is based on gradient ascent. All right, and this equation is based on state or movement. Right? Now, what we do is in this equation, we need to find out what the rate of change of Q is with respect to time. Now, the rate of change of Q with respect to time is given by, we're using this equation here, just make a movement involved here. Okay. And the movement is basically telling us
सही है सर.
if you plug this in over here, and so you can simply get that because this is the new value of Q based on the movement, and this is the old value of Q before you made the movement. Does that make sense?
Okay, you are saying कि ये new value है और आप उसको old से subtract कर रहे हैं.
So we basically said previously that we're going to take the current value, the new value of Q, which is this, is over here, and the current value is this, okay? And we're subtracting it to be able to get the rate of change of Q. Is that making sense? Okay.
Okay.
So let's move on. So now basically we've combined these two equations, one based on temporal and the other based on movement, and we've essentially got it. Now the best way to understand this is by looking at a simple example. I think that will make it a lot clearer. So, and this is, by the way, the full final algorithm. It looks sort of like this. We've already covered most of it. Q new, we take the original value of Q. We take the learning rate. We have a plus sign because we're using gradient ascent. And then we have the reward. This term we've looked at, this term we've looked at. Now, a discount factor is also put in at times because the future rewards that you get sometimes are not very useful. Okay, so it's sort of like the time value of money. A rupee earned tomorrow is not the same value as a rupee earned today, right? We all understand that. There's inflation. So if, for example, you want to discount future rewards, you may have this as 0.9. Let's say if you have 10% inflation, you might say that, you know, if I'm going to get a reward of 100 rupees next year, it's only going to be worth 0.9 of its value, right? It's only going to be worth 90 rupees. And if I get a reward 2 years later, it's going to be worth 0.9 squared. You know, every year, let's say there's a 10% inflation, then that's going to be worth only 81 rupees. Okay, so this is sort of a discount factor which looks at the reduced value of future rewards. Okay, so I hope that is clear. That's an additional term that is often included. All right, I'm going to keep moving forward. So this is sort of a summary of the whole thing, which gives it all on one page. It's also from Jeff Heaton's notes, so you can refer to that as well. Now let's take a simple case, and I'm going to make some simplifying assumptions, okay, so that we can understand it very simply. So let's assume that alpha, the learning rate, is 1. Okay, remember we did that in one of the homework examples. When we're doing the weights, I think we did that. That simply means that, you know, the learning rate is going to be big. It's not very small. We're also going to take the discount factor to be equal to 1. So we're going to say there is no time value reduction in the reward. G.
Will this discount factor be between 0 and 1?
Yes, so both of these are between 0 and 1. So gamma is between 0 and 1, right? And the learning rate can actually be, doesn't have to be between 0 and 1. So learning rate could be anything. Yeah. But discount factor is definitely between 0 and 1 because you normally discount the future rewards. I can't think of a case where you want to, instead of discounting the future rewards, you want to, if you have something called negative inflation, then in that case, you know, sometimes it happens that wo Pakistani rupee, the dollar actually goes down. And so the Pakistani rupee goes up. So that's the case where the value of gamma can be actually greater than 1. This is a gamma.
So this is why I was asking.
So normally it's between 0 and 1, but it doesn't, I guess it doesn't have to be. Okay. So let's make the So let's make the simplifying assumption that gamma is 1 and alpha is 1. Okay. If you do that, the equation becomes a lot simpler. Okay. It simply becomes these two cancel out. All right. Because this is 1. And you're simply left with, and this becomes 1. So you're simply left with R, and you're simply left with these two terms. Okay. So this is simply saying that we're going to take, and this is what we've actually been doing. In the past, if you looked at the past examples, when we made a movement, we said we take the movement cost and we take the maximum of the adjacent cost. Okay. So this was the simple example where we don't have learning rates. So now let's take a look at go back to the simple grid world example. We're going to look at the case where alpha and gamma are equal to 1. And now we're going to, instead of using our intuition, we're going to use the Q-learning algorithm. Okay, so the Q-learning algorithm that we're going to use is basically what we've just derived for the simplified case, that Q new is simply going to be equal to the previous, to the reward and the maximum value of the adjacent states. But now what we're going to do is we're going to start off initializing it to some random value, or as is normally done, we initialize it to 0. Okay. So let's see if we can do that. This is a simple table that I'd like you to help me fill out. What I'm showing here is this 4 states. It's a 4-state grid example. S1, S2, this is S2, this is S3, this is S4. I've shown this as a little smaller because these are terminal states. You have a reward of -1 here, a reward of +1 over here. And you start off by making the Q values equal to 0, all the Q values. And remember, the Q value in each state depends on the direction as well. So if you, from state S2, you go upwards, you get a cumulative reward of 0 initial value. Here you get an initial reward of 0. And from here, if you go downwards, you get a reward of 0. From here, if you go upwards, you get a reward of 0. That's your initial value because we want to start off somewhere. Now, can somebody help me improve this? So what would the new value of Q3 taking the up action be? Any suggestions?
So it would be +1 because maximum of Q will be 0, basically.
Achha, dekhiye, there is a movement cost as well. So we said movement reward is -0.1.
Okay, then it would be 0.9 if I'm not wrong.
So it would be -0.1 for the movement +1 because once you get here, you get a reward of +1. All right, so this is the reward over here. Plus, we're saying the maximum value of the next stage. Now, in the next stage, you don't get any further rewards, okay, because this is a terminal state. So we're going to say there is no further rewards, okay? So this is simply going to be 1 minus 0.1, which is going to be plus 0.9, okay? Now, let's take a look at the next one. Any guesses over here what this would be? We're using this equation.
0.8.
So can you tell me what the equation is?
Minus 0.1 plus, oh, I'm sorry, 0.9. And
minus 0.1. And now we're taking the maximum value of the state, the next state where we're going. So we're going over here, okay? And we're going to take the maximum value of the Q values in both of these states. What's that?
0.
There's going to be maximum of 0 and 0, right? There are two possible actions that you can take in state S2. And both of them currently have 0 values. So what is this going to be equal to?
Minus 0.1.
Minus 0.1, right? So earlier we jumped directly to negative 0.7 or something, but here because these values are not updated yet, we can't really get to that final value. Okay. Now, can you update this? What would this be?
0.8
minus 0.1
Minus 0.1
plus max of 0, 0.
plus max of
0 and -1, if I'm not wrong.
minus 0.9 and minus 0.1.
You see, now we have these. We're taking the, we're basically saying what is the maximum value of the next state where we're moving to, st plus 1. We're moving to state s3. And what is the q values of E? We're looking at both both the possible actions. So if you go up from here, it's going to, the q value is currently 0.9. If you go down from here, the q value is negative 0.1. So you're basically taking the maximum of 0.9 and negative 0.1. So what's the answer?
0.8.
0.8.
So this is 0.8, and it looks like the final answer that we got earlier, right? This doesn't look right. This seems like this is probably going to change. This looks about right. If you recall, this was coming out to be 0.9. Now, can somebody do this one?
Minus 0.1 and max of 0, because we don't have still, like, we don't have any rewards. It's the terminal state.
Is this right?
So -1.
No.
That -1.
Minus 1 bhi aayega na, because the actual reward is there's a movement cost, and then there's a reward of -1 over here. Just like we had the reward of +1 here.
Yes.
So what is this going to be?
-1.1.
Okay. So this also looks like it's final. Now let's do the next iteration. Okay. So so this was the first iteration. Now we're going to continue doing this.
Sir, just second वाला है सर जो सेकंड वाला रॉ है उसमें मैक्स ऑफ 0, 0 वाली बात समझ में नहीं आई मतलब कौन से दो जीरोस की बात
Okay, these are these two zeros. Okay, so let me draw it. ये दो जो zeros हैं, these are these two zeros. Okay, it's the q values of the state where you ended up, st plus 1. So it's the q values of st plus 1. All right, in st, let's say this was at time t is equal to 0. This is time t is equal to 1. This time t is equal to 2. All right. So basically what we're saying is that in this particular equation, what we're saying is that s of over here, this was s of t plus 1 basically becomes.
सर मतलब जिस स्टेट में जा रहे हैं
जी
जिस स्टेट में लैंड करेंगे उसमें क्या क्यू वैल्यू है
हाँ yeah, I think this is a little confusing. Let me not put the t values over here. Yeah, so basically from here, if you take this action, down action, you end up in the state below, all right? And you look at the q values in the state below. Okay, you look at the q values in the state below, and you look at the maximum of those two. So you look at the maximum of this and this. Okay. Similarly, with this maximum was the maximum values over here. All right, of this state. But since this is a terminal state, this was 0. Similarly, this is going into the terminal state, so this was 0. But these two are not going into terminal state. So ye jo hai, this is based on what? This is based on these two guys. Okay, because you'd
Okay,
already
sir.
calculated this. So you have these two. ये दोनों हमने calculate नहीं किया था, तो we didn't have this because it's an iterative process. Does that make sense? So let's
Yes,
do
sir.
the
Clear हो गया मुझे.
ठीक है. Now let's do
So
this.
basically now for this one we won't have any change because the max 0 would stay the same.
Yeah, exactly. So this would be minus 0.1 plus 1 plus maximum of 0. So this would remain to be 0.9. So we've actually found the optimal value already over here. Okay, let's calculate this now. The Q3D, what would Q3D be?
Minus 0.1
Minus
plus
0.1.
maximum of 0.8 and
minus
minus 1.1.
Right. And this would be
0.7.
0.7. So now you can see we basically got the same results that we had earlier. Remember we had, well, this was a more different example, but you remember that we got 0.7 over here and 0.9 over here, and we had 0.8 over here. Okay, so this looks very similar to that. It's a slightly different example with less states, but the results are more or less the same. So 9 and 0.7, ये भी change नहीं होगा, right? Because this is negative 0.1 plus maximum, नहीं हो सकता है change हो जाए. Let's double check. What would this be the maximum of?
Minus 1.1.
Sorry?
Minus 0.9 and
Minus 1.
नहीं,
Point
0.9
सेम
and
रहेगा
minus
0.9
up.
पॉइंट माइनस 1.
0.9 and
0.7.
0.7.
0.7 होगा, right? Because we're
Okay,
taking
that's
these
a
two
previous,
values.
right?
So you're basically saying that the Q value of going upwards will be, there's a movement cost. And then from here, what is the maximum that we can get? Maximum. So if we go up here in this direction, we get 0.9. If we go down from again back, coming back, we get 0.7. So we're looking at the maximum of these two, which will now give us, actually it will not change.
0.8.
So the result remains the same. Although the equation changed, but the result remains the same. Okay, so this is the same as this. This one again would not change, right? Minus 0.1 minus 1 plus maximum of 0. Negative 1.1. So basically what we've done is we've now got convergence. So all of these are now the converged results. Okay. And you can continue doing this iteration, but it will not impact the result. And after you've done a few iterations, you can tell that the results are not changing and you've probably hit the minimum value. The minimum value, the max, this was the maximum value of Q. Okay. So basically what we've done is for every state, we now know what is the best action. So if you're in state S3, the best action is to go upwards, all right, because the Q value of going upwards is 0.9. Similarly, of state S2, the best action is to go upwards because the upward Q value is 0.8. Okay, it's a very trivial example, but it shows you the actual calculations going behind the Q-learning algorithm. Okay, everybody all right with this particular example?
Yes.
Yes, sir.
Okay, so now let's see how, and this is the thing which I had already solved. Now, let's make it a little bit more complex. Now, let's include probabilities. Okay, so, and this is where Markov decision processes come in, because we earlier, remember, we said that when you're going up, there's a certain, you don't necessarily go end up in the state above you. There's a 20% chance that you actually go in the wrong direction. All right, there's 80% chance that you go in the right direction. And here you're trying to go down, there's still a 5% chance that you go in the wrong direction, okay? So how do we handle that? It's fairly straightforward. Basically what we do is, if you remember this equation of Q, all right, so here we had Q is equal to R plus the maximum over the Q value of adjacent states. Now what we're simply going to do is we're going to take the expected value. Okay, and for this simple example, this is assuming that alpha is equal to 1 and gamma is equal to 1. All right. So all we've done is we're going to take the expected value. Now I hope everybody understands what expected value is. Whenever you have probabilistic situations, you simply take the expected value. Okay. So we're going to take the expected value of the reward. Right. Now there's also a Bellman optimality equation, which is often referred to whenever you talk about Q-learning. And what this says is something interesting. And we look at more examples of this as we go forward, but let me just introduce the Bellman equation over here. It basically says that the optimal equation for Q will satisfy this equation. Okay. It will satisfy this equation. In other words, if you know what is the optimal values in the subsequent states, in the adjacent states, all right, and you take the maximum of those plus the movement reward, then this will be the maximum, the best that you can do in this particular state. It's sort of quite intuitive and quite obvious that if this is the best that you can do from the adjacent states, then the best that you can do from the current state is simply the maximum of that value, plus of course the movement cost. Okay, does that make sense to everybody? Is this quite, it seems so obvious that it shouldn't even have a name, but it's got a fancy name called Bellman equation. Does everybody understand this equation?
Sir, I don't understand the OR equation, which includes the discount rate.
Okay, so remember when gamma is not equal to 1, we had a discount factor. And this discount factor is coming in because when you get future rewards, as I said, the value of future rewards may come down. Okay, so if it's 0.9, then you're going to multiply it by 0.9. So future rewards may have a slightly discounted value.
Okay, sir.
Okay, but this is it's actually quite an important equation as well, because now we're talking about the optimality. All right, this is the optimal equation. So what it's saying is that if you know the optimal equation from the next state, if you know the optimal value of Q in the next state, then in a sense, you can figure out what is the optimal value in the current state. So this is the optimal value in the next state, okay, t plus 1, all right? And you take in the maximum over all of these actions. Then the optimal value of Q in the current state is simply this value. You can maybe go in different directions over here. You take the one which is the best. Suppose this is the best, which is the maximum value over all actions, and you simply add the movement cost. Okay, the reward that you get when you go from this state to this state. So this could be state ST, and this could be, let's say, a state ST plus 1. So this is quite intuitive, but it does have a fancy name. So so now let's go back over here. And let's see if we can take a look at a simple example which looks at probabilities as well. Okay. So let's look at this example. And this is again from one of the online lectures that I found. I think I've got a link somewhere over here. Basically, the example here is that when you're moving in a particular direction, then if there's a 90% chance that you will move in the desired direction. All right. In the desired direction, you will get 90% chance. But in the opposite direction, there's a 10% chance that you might go in the opposite direction. Okay, this is sort of similar to the example that we had earlier of trying to go up and go, you end up going down. There is also a movement cost, okay? And there's a final reward of +1 in state S3, okay? And there is a -1 reward of being in state S1, okay? So a very trivial example. But now it does have probabilities, okay? So let's see how you would calculate the values of Q. So this is now the expected value of the rewards. And the way we would calculate the expected value is you would say you get a certain reward. Let's say you get a reward of going upwards, okay? And then you multiply it with what is the probability of going in that direction. You start with a particular state in the state ST. You take an action A, and there's a certain, now it's not 100%, there's a certain probability that you might go in the opposite direction, right? And the reward associated. So all you're simply doing is you weighting the reward with the probability of going in that direction, okay? So let's see if we can calculate this. What would be Q2U? So I'm using this notation Q for this notation. So I'm just writing it small q over here. What would be Q2U, which means the cumulative reward of being in state 2 and then going upwards and taking the action of going upwards. Given that now there's a 90% chance you'll go upwards, but there's a 10% chance that you'll go downwards. Can somebody help me with that? Remember, it's going to be a sum. So that it's going to be sum of two possible directions, right? All right, so let me help with the first part. So let's say you go in the upward direction, that's a 90% probability, 0.9, that you start in state 2 and you take action upwards and you get to state 1, 90% probability. And the reward that you get is what? You get a reward of +1 minus 0.1, plus a movement cost as well. That's your reward, which we did earlier as well. Now, the only thing is now we're saying that this is not the only possible direction you could end up in. There's a 90% chance you will go in the desired direction.
This would be point.
Yes, we'll do the sum.
-0.1.
Yeah, we'll do the math arithmetic later on, but it's going to be +1 minus 0.1, which is basically 0.9 times 0.9. Plus, you could actually go in the opposite direction as well. There's a 10% chance of that as well. So what do? We multiply, do a weighted sum, 10% chance of going in the opposite direction. And what's the reward of going in the opposite direction? It's -1.
And it would be -1.
-1.1, right? Because we know that there's a movement cost as well, right? There's a movement cost. So, so this is what it would be, plus the maximum of where you end up. And we know that the maximum over here is 0 because in the next state, that's a terminal state, you don't get any further rewards. So this comes out to be what? Can somebody do the math? .81.
0.7.
Sorry?
0.9. 0.7.
0.7 sounds right. Okay, so let me just double check. Okay, we'll double check. What about this? As long as the equation is right, we don't really care what this is. Can somebody tell me what the equation for this would be? Now we're calculating the Q values with on a probabilistic basis.
-1, minus point,
Sorry,
-1,
minus
minus
1.
point,
minus 1 into minus point.
-1 into
In 0.1.
0.9.
0.9. So we're talking about, let's say you're going downwards, right? So there's a 90% chance that you'll go in the desired direction, right? And the reward in the desired direction is what?
-1, minus 0.1.
Yeah, so it's minus 1.1 plus plus what?
1 minus 0.1 into point.
Plus 1 minus 0.1
Minus 0.1 into
That's
0.1.
into 0.1.
into 0.1, right? So there's a 10% chance that you'll go in the opposite direction and you get a reward of this. So somebody can calculate this. I think I've done the calculations in the subsequent slide. Yeah. So it's 0.7 and negative 0.9. Okay. So this was a simple example which simply shows you how you would do it if you have probabilities involved. And this is actually in the Markov decision processes, you always have certain probabilities. As we saw earlier in the example with the car example and other examples that we've seen, you will have certain probabilities of making certain transitions. So now let's move on. These were two examples. I think these are other examples that we'll skip over. Yeah. So now let's take a look at, now that we've understood what Q-learning is, now let's take a look at a concept which is called exploration versus exploitation. Okay. And this is an example which is given from this particular site. This is a similar example in which they're showing that here's the agent, which is a lizard. Okay. Now the grid world is a square. You can either go in this direction and this direction, or you can go here and you can go here, or you can also go here. And here the bird kind of eats you up. You can go from here to here as well. And you can also go in all kinds of directions, right? And then you can go from here to here and so on. So now it's a two-dimensional world, not one dimension anymore. And you can go in all kinds of directions. So the question is that the issue over here is that there are several issues. The first issue is that if you look at this, we can use this particular table that we've already seen somewhat. And this is what is referred to as a Q table. All right. And what basically this shows is on the vertical axis over here, it shows the possible states. On the horizontal axis on the horizontal side, it shows all the actions. And initially, as we had done earlier, it has all the 0 values for all the Q values. So just like we had done over here, basically we had Q, and I hadn't shown this separately, but you can show these different actions horizontally as well. So this is how it is typically done, is that you keep on updating these. Okay, so for example, if you're updating this, you come up with a new value and so on, okay, as you keep on updating this. Now, the point that is being made over here is that the way this is normally done, and I sort of didn't go over this completely, is that as you're trying to find the optimal, as you're trying to do this iteration, over here, what we had done is we had looked at both possibilities of going upwards and going downwards, right? So we had done an iteration in which we had looked at both the possibilities, and there were only two possibilities in this case, up and down. Now, what if the number of possible actions is extremely large? Okay. And the examples that are typically given is, for example, if you you playing a game, one of those strategic games, or even if you're playing chess, for example, the possible actions in any given state, first of all, the number of states is very large, and the possible actions that you can take from any particular state is extremely large, right? You've got 16 different pieces, and each one of them can move in various directions. So, so you could have a very large state space. Now, the question is that if you look at this example over here, yeah, so let me go back over here. So the way you update this is that you go in a particular direction, all right? So here what we were doing is we had these states, and we went in a particular direction and we updated the Q values, right? Then we went in a different direction and we updated these values, okay? Now what can happen at times is that you've gone in a particular direction. So let's say you have a grid now. Let's go back to this example. And let's say that you've gone in a certain direction. Let's say you've gone in this direction initially, all right? And you find a single cricket, and that gives you, let's say, a reward of +1, okay? And you figure out that going in this direction is not really helping you, but this direction is giving you rewards, okay? Now, because it's giving you some immediate rewards, you may never think about going and exploring other directions as well, okay? Because the reward over here is not positive, the reward over here is positive, but this reward is not positive, okay? So you are actually losing the opportunity of getting this reward, which is showing you as a +5, okay? This is showing you as 5 crickets, all right? So initially you went in this direction, you got some good rewards, and now what you're seeing is that this is the best direction to keep on going, and I'm going to continuously keep going over here. And maybe when you go in this direction, you find out that there is no point going over here. I'm going to come back over here, all right? We're going to avoid going in this direction. We're going to avoid going in this direction. But it seems like your world is limited to this region, okay? Do people understand what I'm trying to say? That you found some reward, and there is some reward which is in a remote region, but you're actually not exploring that. Simply because there's so many different paths, so many possible actions that you can take, that you're not really exploring all those possible actions, okay? And you get into it's sort of like finding a local maximum, okay? And you're not looking at the better maximum. Or it's sort of, when we're looking at losses, we've got stuck in a local minimum, you're not looking at the optimal minimum. So when you get into this situation,
Sir, what about the momentum?
So इसमें momentum नहीं इस्तेमाल हुआ है. That's a good point, but if you remember, we haven't really, that's a good way to think about it, कि हमने पहले momentum इस्तेमाल किया था, लेकिन अभी तक हमने momentum का concept अभी यहाँ तक इस्तेमाल नहीं किया है. Okay, because this is a little different from the previous examples. Maybe you think a little bit deeper, but we're not really using momentum over here. So the idea of exploration versus exploitation is that in exploitation, what you do is, if you found some good solution, okay, you stick to that, all right? So we found some good solution over here, and maybe we're just going to stick to that. So this is saying exploitation. We're going to find something, and we're going to continue to exploit it, okay? Exploration, on the other hand, is basically saying that we're not going to just stick with the nice, comfortable region that we are, but we're actually going to explore, okay? We're going to go in different directions. And the question is, when you're trying to update your Q values, do you do exploration or do you do exploitation? Okay, how do you update your Q values? So the solution is what is referred to as an Epsilon-Greedy strategy. And what that basically says is that we're going to use a parameter called epsilon. Okay, you can see the epsilon over here. And we are initially going to make it very high. We might actually make it 1. Okay, at time t is equal to 0, we make it very high. And epsilon is basically the probability. Epsilon is the proportion of time exploration will be chosen over. Sorry, I've got that wrong. It's the proportion of time that No, I do have it right. So yeah. So it's the proportion of time that exploration will be chosen over exploitation. Okay. So initially, we're going to be very adventurous. Okay. We're going to be exploring because we really don't know the environment. So we're going to say, okay, we're going to initially go in this direction. Then the next time we're going to, even though we found a good solution, we're going to keep on exploring. Okay. We're going to explore the entire region. So we're going to have an epsilon of a very high value of 1, which basically means that we're going to toss a coin and we're going to decide which direction to go. Okay. And so initially the epsilon value will be kept to 1. But as we learn more about the environment, we're going to start reducing the epsilon value. Okay. So we're going to slowly keep going downwards. All right. So as we become more and more comfortable with our environment, we know that we've explored the whole region. We don't need to actually explore so much because exploration is not really going to give you so much value. We're going to start exploiting what we've already got. Once in a while, what you might have is a change of the environment. Okay, so if an environment changes and all of a sudden you've gone into a region which you haven't explored before, you might want to make the epsilon value go up again. Okay, and you want to start becoming adventurous and start exploring the new territory that you haven't really looked up. Okay, so this is basically the concept of epsilon-greedy strategy, and this is used as part of the Q-learning phenomena. If there's no question about this, let me just try to now wrap up. And now the last, actually we have 5 minutes left. Now let me just link how does this link to the concept of deep learning. All right, so far we haven't really talked about ANN or deep neural networks at all. We just talked about the classical reinforcement learning. But the interesting part is that the deep Q network or the deep learning part is fairly straightforward. Okay. Now the issue here is that if you have a small state space, okay, so if you have a small state space, for example, the number of states and the number of actions are very small. As we saw in the earlier example, the number of states was, let's say, 4 or 5, and the actions were just up and down. So you had 2. So simply the state space was simply 10. All right. So the Q-learning algorithm could be fairly straightforwardly applied. However, if you have, for example, an extremely large state space, okay, so you can imagine that if you're playing a game of chess, then the state space could be extremely large. The number of actions could be extremely large. So how do you update the Q values? And that becomes very computationally complex. Okay. So the idea simply is that we're going to try to approximate the values of the Q values. Okay. So earlier, what we were doing is we were actually manually calculating the optimal Q values using this particular table. All right. So if you saw this, we were iterating through and finding the updated Q values using a complex table. And you can imagine that this becomes extremely computationally extensive. Right. So basically, when the state action pair is extremely large, as in real cases, what we use is a DQN or a deep Q network, which is basically the combination of Q-learning with a deep neural network. How that is done is fairly straightforward. So this depicts a deep Q network. Essentially what you have is states are entered as input into a deep neural network. And this is the deep neural network, your traditional deep neural network. And the output is all the possible Q values for every possible action corresponding to this particular state. So let's say that there are 4 actions possible in this particular state. There would be 4 possible Q values. And the way the loss equation would be calculated is that it would compare the output value, the output Q value of the deep neural network with the optimal value. And the question now is, what is the optimal Q value? So the optimal Q value will be based on the Bellman equation. So it will use this particular equation, which we've already seen in the previous portion, and it would, excuse me, it would use this to calculate the loss equation. Once the loss equation is calculated, the usual gradient descent and the backpropagation algorithm would kick in, and you would calculate the updates of the weights. So here's a simple example that was given as per this particular YouTube link that I've given. So here the example is of an Atari breakout game. And here the important point is that not only do you give an input as a single image, but you give a whole stack of images, so that the particular so that the input can actually determine the state, the environment can actually be determined based on this entire series of inputs, so that you get some idea as to what's actually happening in the game. So the first frame is followed by the second frame, which gives you an idea that the ball, for example, here is moving in the upwards direction. And maybe it gives you an idea of how fast the ball is moving, or how in which direction the paddle is moving. And so the set of 4 frames is given as a single input. And for that particular single input, the deep neural network tries to predict the optimal, the Q values corresponding to all the possible actions. And let's assume that in this case, 4 actions are possible in the 4 different directions. So it would give you the Q values in 4 different directions. So that's pretty much how a deep Q network works. And that ends our particular section on deep Q networks and Q learning. Thank you very much.